Hello friends, today we are going to derive the expression for the Schrodinger's time dependent wave equation. It is also called as the Schrodinger's fundamental wave equation, or also it is called as the Schrodinger's amplitude wave equation, or the Schrodinger's steady state form wave equation. So this equation is very important as far as quantum mechanics is concerned. It is the fundamental equation. It is the fundamental equation in the quantum mechanics, and that can be used to solve the many problems, or in order to solve the applications of the quantum mechanics. Here we can use this Schrodinger's fundamental wave equation. This is important equation. It does not include the time factor. It is time independent, not dependent. It is time independent. We will see time independent wave equation. Independent wave equation. It is also called as Schrodinger's fundamental wave equation, amplitude wave equation, or steady state form equation. So last time we have seen this Schrodinger's time dependent wave equation. This is I h cut delta psi by delta t minus s cross square divided by twice m d square divided by dx square plus v, that is potential energy of the particle, into wave function here. So in this equation, here the h cut is reduced to Planck's constant. Here the h cut is reduced to Planck's constant. It is equal to Planck's constant divided by twice pi. It is called as reduced to Planck's constant. Here the psi is nothing but wave function associated with the moving particle. It is nothing but what here? The wave function. The wave function associated with the particle. M is mass of the particle. Here this is M is mass of the particle which is in motion. Here the V is nothing but here the potential energy of the particle. V is nothing but here it is the function of x and t. Here you have to remember, this is potential energy of the particle. Potential energy of the particle. So here the potential energy of the particle is function of position as well as the time. But in many situations or in many problems, it is observed that this potential energy of the particle depends only on the potential energy of this particle depends only on the position of the particle and not the time here. So if this is true, so potential energy of the particle varies with only position of the particle. Position of the particle changes, the potential energy changes here. So if this is the case, in this case Schrodinger's time dependent wave equation, potential energy is function of position as well as time. But in many situations or many problems, the potential energy of the particle depends on the position of the particle only. So potential energy varies only with the position of the particle. If this is the so case, then we will here derive this Schrodinger's time independent wave equation. This is dependent wave equation. We will derive this Schrodinger's independent wave equation from Schrodinger's time dependent wave equation by removing all the reference to the time. So all the reference to the time. So all the reference to the t we will remove from this equation, and that equation becomes this Schrodinger's time independent wave equation. So for that, consider the particle, consider the de Broglie's wave. De Broglie's wave is associated with the moving particle. So if suppose this is the particle of mass m here and it moves with velocity v here, then the wave system is associated with it like this. Then the wave system is associated with it. And the quantity, this wave is called as de Broglie's wave or the matter wave. This wave is called as, we are knowing this is the matter wave. The wave associated with the moving particle is called as here the matter wave. Here. And the quantity which characterizes this de Broglie's wave is known as, we are knowing here, this is the quantity which characterizes, which describes the state of this wave is known as the wave function here. So now the value of this wave function in terms of the value of this wave function in terms of here the energy of the particle. If suppose m E is nothing but total energy of the particle here, and V is nothing but the potential energy. Suppose the P is nothing but, which is function of x only, we will take later on here, and the P is nothing but momentum of the particle. It is equal to product of mass and the velocity here. So these are the physical parameters of the particle. So physical parameters of the wave also we will define, that is frequency, its frequency, that is mu, its wavelength, that is nothing but lambda, its time period, that is t, and so on. So we can write the value of the wave function in terms of these parameters associated with the wave, or it is equivalent to define also the wave function in terms of the parameters of the particle. So we will define in this case now the wave function of a wave associated with the moving particle in terms of the energy and the momentum of the particle. Physical parameters of the particle, last time we have seen how it is comes. So it is nothing but amplitude of the wave, that is A into e to the power minus I divided by h cut, I divided by h cut into bracket et minus px, total energy of the particle into time here minus momentum of the particle into x, et minus px. So this is the equation. So what this equation? The wave function which characterizes this de Broglie's wave in terms of the energy and momentum of the particle can be written in this way. Now this equation can be written as, we will separate this equation with time dependent quantity and time independent quantity. So that will be equal to A into e to the power here we will introduce I minus I by h cut to the inside. So we are getting minus I et here, minus I et divided by h cut into e to the power again. Here e to the power, introduce this to this side, minus become plus. So ipx, here we are getting ipx, here ipx divided by the h cut. So we are getting this equation here. Now for this equation, this will be equal to, so the wave function, the psi will be equal to A into this term, we will keep it as a psi 0. It is equal to psi 0 into e to the power. So what we have done is that we have separated this. This is time dependent quantity and the other is nothing but what here? The time independent quantity. So e to the power, here the minus I e t divided by h cut. And suppose this is the equation number 1c. Here the psi 0 is equal to what quantity? This is where the psi 0 is equal to, in this equation, where the psi 0 is equal to A into e to the power minus ipx by h cut, e to the power minus ipx here divided by h cut. So we are getting this particularly. So this is the equation 1 here. Now so equation 1 gives the wave function of a particle here. So psi is equal to like this equation we are getting. Now differentiate this equation with respect to t. So we are getting here delta psi by delta t. So what we are getting? Delta psi by delta t will be equal to differentiating equation 1 with respect to t, we are getting delta psi by delta t. So this will be equal to here. So psi 0 is here. It is independent of t. That is, it can be regarded as constant. So psi 0 into e to the power, this differentiation of this as it is, and then differentiation of this power term. So e to the power here minus ie t also as it is divided by h cut divided by h cut into differentiation of t. So coefficient we are getting, that is the coefficient. So into bracket minus IE here, minus IE divided by h cut. So this is the differentiation of power term here. So differentiating this equation with respect to t, we are getting this equation. Psi 0 e to the power minus IE t divided by h cut into minus IE divided by h cut. So we are getting this equation. Again differentiating this equation. So suppose this is the equation number 2. This is equation number 2. Differentiating this equation 1 again with respect to x. Now twice time. So differentiating, that is we are getting gamma psi divided by now with respect to x. So you are getting like this. So in this equation here is no x. So this can be regarded as constant. We will differentiating with respect to psi 0 only, because in psi 0 there is x. So e to the power, this term is constant, e to the power minus IET divided by h cut, we will take as it is, into differentiation of this, that is gamma psi 0 divided by the gamma x here. So again differentiating this twice time means we have to differentiate this equation again. So we are getting d square psi divided by dx square. So this is equal to dx square. This will be equal to this term as it is, e to the power minus IET divided by h cut, IET divided by h cut here, divided by h cut into differentiation of this. So we are getting d square psi 0 divided by dx square. So we are getting this equation dx square. So suppose this is the equation number 3, say this is equation number 3 here. So this is equation 1, 2, 3 we are getting from equation 1, and differentiating with respect to t, differentiating with respect to x twice time, we are getting these equations. Now record this Schrodinger's time dependent wave equation. That is, we are knowing I h cut, Schrodinger's time dependent wave equation in one dimension case. So gamma psi divided by gamma t. So this will be equal to here minus h cross square divided by twice m d square divided by dx square plus potential energy into psi. So this will be equal to here psi we have to introduce in the bracket. So minus h cross square divided by twice m here d square psi divided by dx square plus phi psi, here the phi psi. So we are getting this equation. So suppose now this is the Schrodinger's time dependent wave equation. Schrodinger's time dependent wave equation. This is. Now with the help of equations 1, 2 and 3, this equation become. So this is I h cut, which implies gamma psi divided by gamma. So we are getting this equation. Now we will put the value of gamma psi by gamma t from equation 2, gamma square by gamma x square from equation 3, and the value of psi we will take this. So from equations 1, 2 and 3, this equation become. So what it becomes? I h cut as it is. Here gamma psi by gamma t. Instead of gamma psi by gamma t, we will take now this term psi 0 here, the psi 0 e to the power e to the power minus I by h cut minus I e here minus I e t here divided by h cut into here minus I e divided by h cut. Now this will be equal to, so delta psi by delta t we will put this value. Now minus h cross square divided by twice m, here the minus h cross square divided by twice m as it is into here delta square psi divided by delta x square. So from equation we are getting this e to the power again minus I e t divided by h cut into d square, here d square psi 0 divided by dx square here. So dx square, so this, and again phi psi plus phi psi here, the plus phi psi, so plus phi as it is, and the value of psi we will write from equation number 1. So here is psi 0 here e to the power minus I e t divided by h. So we are getting this. So from putting the values of delta psi by delta t, delta square psi by delta x square, and psi from equations 1 and 2 and 3, we are getting this equation. Now this equation how becomes? What we have to do is that here now dividing entire equation by e to the power minus I e t divided by h cut here. So dividing that equation, so dividing this equation by the term e to the power minus I e t divided by h cut, divided, if we can divide this get cancels, here get cancels, this get cancels, and simplifying, what we will get is that here is I become I square, and it becomes minus 1, and this minus and that minus become plus 1. Here h cut get cancels, and e, so what we are getting is here is e psi in this equation. So dividing entire equation by this term and simplifying it, what we are getting is, simplifying means h cut get cancelled, I become minus I square and I square become minus 1, and already there is one minus I become plus. So we are getting remains only e, and here the psi 0 is equal to, so e psi 0, this will be equal to here the minus h cross square divided by twice m, this get cancels, remains next term, that is delta square psi 0 divided by delta x square. So remains this delta x square plus here this term get cancels. So what we are getting is phi psi 0. So what we are getting, dividing entire equation by this term and simplifying, we are getting this equation. Now this will be equal to, which implies here we will take all these terms to this side. So what we are getting is minus become plus h cross square. So we are getting here the h cross square divided by twice m into d square psi 0 divided by dx square plus e psi as it is, e psi 0 plus phi psi here become minus. So minus phi psi 0 is equal to 0. So we are getting like this equation. Now this will be equal to minus h cross square divided by twice m d square psi 0 divided by dx square here, plus we will take common psi 0. So e minus here is nothing but phi psi 0 is equal to 0. And finally we are getting here from that equation, so which implies here we will multiply this equation by twice m divided by h cross square, twice m divided by h cross square, so this get cancels, so remains is nothing but d square psi 0 divided by dx square here plus twice m divided by h cross square into bracket E minus potential energy, that is V into psi 0 is equal to 0. And this equation is known as the Schrodinger's fundamental wave equation. So delta square psi 0 divided in one dimension. It is usually written in the form. In that equation, phi is function of x only. Now, it depends on position of the particle only. Here, the potential energy of the particle in this case depends only on what here? It is the function of x only now. So, this can be written in usual form as d square psi divided by dx square. So, by omitting only 0 here, this will be equal to twice here plus twice m divided by h cross square into bracket E minus V potential energy psi will be equal to 0. So it can be represented by this equation. This is one dimensional case, and in case of the three dimensional case, this can be written as, this equation can be written as d square divided by dx square plus d square divided by dy square plus d square divided by dz square here, instead of d square divided by d square like this, psi as it is here, psi as it is plus twice m divided by h cross square into bracket E minus potential energy, that is V psi is equal to 0. So is equal to 0. We can write like this equation in case of three dimensional case, and which implies this is nothing but Laplacian operator, that is del square psi plus twice m divided by h cross square in bracket total energy minus potential energy, means we are getting kinetic energy. This is the wave function psi is equal to 0. So this is the famous Schrodinger's fundamental wave equation in three dimensions. This is three dimensional the equation. So in this lecture we have seen the important equation, that is Schrodinger's fundamental equation, and this equation we are going to use for the many applications. In the next topic, applications of this Schrodinger wave equation, we will use this equation, because in many problems of this situation the potential energy does not depend on the time, and that can be solved by using the Schrodinger's time dependent wave equation and removing all the reference to the time. In this way we will derive this equation. So this is Schrodinger's fundamental wave equation. Okay, thank you.